elastic behavior of materials. Under this, we learn elasticity and plasticity. Elasticity. Here you have a rubber band. This deforms when you apply a force. When the applied force is removed, it backs to its original shape. The examples are rubber, metals, steel ropes. So elasticity is a material is elastic if it returns to its original shape after removing the applied force. Plasticity. Here you have a glass. If you apply a force, it breaks. A material is plastic if it does not return to its original shape after removing the force. Elasticity. To understand more about elasticity, we should learn stress, strain. Stress. Force per unit area applied on a body is called stress. Mathematically, stress sigma equals force F upon area A. Here you have a ceiling. Two wires are hanging with area A and A by 2 each. Both are hanging with the same load F. Now, let us find the stress for the first and second wire. For the first, sigma 1 equals F upon A. For the second wire, sigma 2 equals F upon A by 2. As the area decreases, the stress increases. Sigma 2 equals 2F upon A, so 2 times sigma 1. Therefore, sigma 2 is greater than sigma 1. The unit of stress is Newton per meter square, Pascal. The dimensional formula for stress is mL power minus 1 T power minus 2. Types of stress. Longitudinal stress, this is of two types. One is tensile stress due to pulling, the other one is compressive stress due to pushing. Here you have tensile stress. Now let us pull the body with force F each on either side in the opposite direction. Therefore, the length increases and the area decreases. This comes under tensile stress. Sigma equals F upon A. Compressive stress, pushing. Here you have a rod. Now let us push either end with a force in the opposite direction so that the length decreases and the area increases. The stress sigma equals F upon A. Here you have a column, pillar, on which there is a statue. The heavy load of the statue compresses the column. A weightlifter lifts the load. On the upper part of the rod, you have a tensile stress, it's pulling, whereas bottom part of the rod, you have a compressive stress, it is pushing. It's all due to bending. Shearing stress, a tangential force causing deformation. The lower part of the cuboid is fixed, whereas the force is applied horizontal to the upper surface, so that there is a shift in the upper surface to a distance of del x. This comes under shearing stress and the formula is sigma upon F. Volume stress, force applied on all surfaces like pressure. Here you have a cube that's been given a force in all directions, its volume decreases to a smaller value. So sigma, the stress equals F upon A. For every phase, you have a stress. Here you have a hydraulic lift where volume stress is used. Strain. The fractional change in size or shape due to applied stress is called strain. Mathematically, strain epsilon equals change in size upon original size. Here you have different strain. The unloaded rod is there. When you pull, the length increases, area decreases. When you push, the length decreases, the area increases. That comes under compression. And in bending, the tension and the compression happens at the same time. Then you have a shear strain, the shift in the lower and upper surface, and for the torsion, it's a tilt, a twist in the lower and upper part. The combined loads gives too many forces applied in too many directions gives this. The strain has no unit, no dimensional formula. The types of strain. Longitudinal strain is of two types: tensile strain, increase in length; compressive strain, decrease in length. In the first rod, due to the force, the length of the rod increases by an amount del L. This comes under tensile strain. Whereas in the second diagram, due to force, the rod is compressed. Then the length decreases by an amount del L. This comes under compressive strain. Epsilon for tensile strain is plus del L by L. For compressive strain, it is minus del L by L. Shearing strain. Change in shape due to tangential force. Here you have a tangential force is applied on the upper surface, whereas the lower surface is fixed. Because of this, there is a shift of del x or x in the upper surface with respect to the lower surface. It makes an angle theta here. So, the shearing strain epsilon equals x upon h equals tan theta. Volume strain. Change in volume due to applied pressure. Sigma equals minus del V by V stands the volume decreases. The same diagram what we had seen earlier comes again. Elastic limit. Here you have a rubber band. This rubber band breaks when you give a force greater than a maximum value. The maximum stress a material can handle and still return to its original shape is called elastic limit. Beyond this limit, the material deforms permanently, plastic deformation.